Today we'll pick up where we left off yesterday and discuss the saddle point approximation. So our goal is to approximate integrals of this form. So we have a contour integral in function of w, e to the z, function w, and we're integrating with respect to w, and we want to understand the behavior of this integral as z goes to infinity. So generalizations of this problem occur all the time in path integral and functional integral, the path integral and functional integral formulations of quantum mechanics and quantum field theory. So in that case, z often is 1 over some coupling, or Planck's constant if we're doing a semi-classical approximation. And so we'll be interested in integrals that are very much like this. The main difference will be there'll be multiple integrals instead of a single integral. So our goal today is to understand how we can approximate these types of integrals when everything is not real. So we look at an example of an integral like this. It was a real integral, and that simplified some things. So today we're going to look at the case where some of the objects in the integral are complex. And in quantum mechanics and in quantum field theory, we'll often have an I in the exponent. So we're dealing with complex integrals of this type. OK, and the basic approach we're going to use is going to be very similar to what we did yesterday. We're going to try to approximate this integral as a sum of Gaussian integrals. And we know how to evaluate Gaussian integrals. We did that in tutorial on the first day. But in order to do that, we're going to have to swap the sum and integral. So our result is going to be an asymptotic series, as we saw yesterday. So that's what we're going to try to do today. And so the main complication that comes from making this integral complex, as opposed to having a real integral, is for integrating along the contour, the phase could be oscillating. If the phase is oscillating, then we can get destructive interference. So we might expect the dominant contributions to come from regions where the real part of f is a maximum. That's basically the same approximation we made yesterday in Stirling's approximation. As z becomes larger, this integral becomes more and more peaked near the maximum of whatever's in the exponent. The complication that arises in the complex case is, well, you might expect this to be true, but if the phase is changing very rapidly along the contour near a point where the real part is maximum, then there could be destructive interference, and even though the magnitude of the integrand is large, the phases could oscillate so that there's very little contribution from that region. So this expectation will work as long as we're on a constant phase contour. Otherwise, we you get destructive interference. Okay. So what we want, got some contour in the W complex W plane. And we want to approximate this integral as z goes to infinity as being very peaked around the value which f, the real part of f, is maximum. And we want to go along a contour that has a constant phase. So our contour should look something like this. And there'll be some tangent vector to the curve at the point w naught. So this will be where the real part of f is maximum. And so what do we know about the curve in the vicinity of this point? We're on a constant contour curve. So if we're on a constant contour curve, then let's give names to the real and imaginary parts of f. Let's call it u. Let's let u be the real part of f, and v be the imaginary part of f. Then, if we're on a constant contour, constant phase curve, the phase of this integral is determined by the imaginary part of f. So that means that the gradient of v is 0 along the curve. We also know that at w naught, the gradient of u is 0 at w naught. So together, these two facts tell us that f is a critical point. W naught is a critical point of f. And so we know that this point is a local maximum of the real part. The Cauchy-Riemann equations tell us that analytic functions have no local maxima. So that means that if the real part is decreasing along a curve, it's decreasing in the direction t and minus t, then the imaginary part has to be changing in the opposite directions. So there's no local maximum. The real part is decreasing in this direction, increasing in the other direction. And that's where this approximation gets its name. So W naught is known as a saddle point. If we go in the t or minus t direction, the real part f will decrease. If we go in the perpendicular directions, will increase. Okay. So let's assume that we have some contour that passes through our saddle point, and that our contour is a constant phase contour. So we basically now want to repeat our analysis that we did with the Stirling's approximation. We're going to massage this integral, make it into a sum of Gaussian integrals by expanding f near the saddle point. So f takes this form. And why is there no linear term here?
They reduce zero.
Right. It's a critical point. So the linear term vanishes. And so let's write this in another way, this second term. This, in general, will be a complex number. Let's break it up into a phase, e to the I, delta naught, and a magnitude. And so we know that we're going on a constant phase contour. And so the phase is not changing along our contour. So locally, we should have that f looks like something like this. Where over here, we can linearize the path in a small region around C. Linearize C in a small region around W naught. And we'll say that on this linearized approximation to the contour, W is W naught plus e to the I phi t. So here we're going at some angle phi, and t is the distance away from saddle point. So we should decrease as we get farther and farther away from the saddle point. And comparing these two expressions, we see that W minus W naught times e to the I delta naught is equal to minus t squared. So, and in the linearized approximation to C, we're going at the angle phi. So we can rewrite W in terms of t and this angle. So that gives us that e to the 2I phi, e to the I delta times t squared is minus t squared. And that tells us what angle we're going through the saddle point if we want to go along a constant phase contour. So e to the 2I phi, e to the I. Delta is e to the I pi. And so this determines the angle of the constant phase contour. Okay. So now we can use this result and approximate our original integral as being dominated by some contribution in the small region around the saddle point. So with that approximation, our integral approximately, we pull out this constant factor. And let's say in our approximation, the linear in some regime. Minus t1 to t1. We haven't done anything yet to g. And we've got a Gaussian integral then. And we've changed variables from w to t. So all I've done here is said that our integral is dominated by contribution near the saddle point. Yes?
When you say that it determines the angle of the constant phase contour, is that delta naught or phi?
So delta naught is the derivative, second derivative of f. So that's f is given to us in our original problem. So that's saying that's the second derivative at the saddle point.
So it's the phi.
The phi is the angle here. It tells us what direction our contour is going through the saddle point. So phi is what we're trying to find. So we've said that the integral is dominated by the contribution near the saddle point. We can linearize, make a linear approximation of the contour in that small region. And we can Taylor expand f, just like we did in Stirling's approximation. OK, so now we're basically going to do the same thing we did yesterday, Stirling's approximation. We can Taylor expand G. And we can also extend the limits of integration from minus t to t to minus infinity to infinity, because only for some small region around 0 is the integrand large. And again, here I've left out the linear term. Somebody tell me why? Somebody said something I couldn't hear.
Then the integrand would be odd.
Yes. So the g prime, we don't know anything about it. It could be 0, it could be non-zero. But if we have a linear term here, then this is an odd function, and the integral will vanish. And this factor here at the end is just this dw dt. Okay. And this integral is now of precisely the same form that we had before. We've here t is a real variable. So we've basically reduced it to the same form we had yesterday. We did Stirling's approximation. And so our final result, we can just do the Gaussian integration, get factor 2 pi over z, e to the z f naught over square root of minus f double prime w naught g of w, and if we computed the next term, we get g double prime Okay, so what I've done here is just the Gaussian integration. I've done one other thing. So I have recombined the magnitude of f double prime with these factors of phi. I'm using this relation. Using this relation that e to the I delta phi times the magnitude is equal to phi double prime, and that the relation between phi and delta naught, to get minus f double prime here. So I haven't shown that step, but it's 1 or 2 lines of algebra that you can check, that if you combine the phases, the phase drops out. And here I've included the second derivative term, do the Gaussian integration. You can include more and more terms, the dot here. I did leave out the dot terms here in f. So at some point, the higher derivatives of f become more important. Than the higher derivatives of g. But as long as the higher derivatives of g are more important, we'll get, for the next term, we get 1 over z squared, 2 factorial, and square this, take higher derivatives there. Okay. So if the phase drops out, why did I go through the effort of keeping track of it to begin with? Any ideas?
When we are in QFT, that term corresponds to the action, right? Like the F?
Yes. So in the QFT analogy, so what we're often interested in, and we'll explain this all in the QFT course for those of you who haven't seen any QFT. So if we're interested in computing, say, a correlation function, here would you have some number of products of the fields as G, and F would be the action.
Yeah, so when you take the derivative, the double derivative, you are, it's like a master, right?
Right.
So that's why you're taking it out in the here.
Why I'm taking this
Yeah.
factor out? This just arises as the result of the Gaussian integration. So,
Then what did you ask? Sorry.
so I asked why go through the effort of keeping track of the phase if it drops out in the end.
Maybe you didn't know.
Okay.
That's one answer. So certainly for consistency, right? So you would be very right to question whether this made sense if the phase is changing, right? You could get destructive interference. The point of keeping track of the phase and showing that this worked, well, we don't ever have to compute the phase if we know which saddle points our contour passes through. But as you saw in tutorial yesterday, you're usually not given the contour that passes through the saddle points. Or not always. You're not always given the contour that passes through the saddle points. So a crucial question when you're using this saddle point approximation is which saddle points contribute. You might have multiple saddle points, and they might not all contribute. They might not all be relevant for doing a saddle point approximation. And the next thing we're going to do is go for an example where that does occur. We have multiple saddle points, and not all of them will contribute to the asymptotic series expansion of the original integral.
It seems like requiring that C is a constant phase contour would be like a pretty tight restriction on what C can be. Is there some physical reason why you would usually be integrating along a constant phase contour?
So typically, in physics applications, F and G are nice functions that are analytic most everywhere. They might have some poles or branch cuts. We might, when we get a integral like this, we might have in mind some original contour. That original contour is not always going to be the one that is applicable. And a contour in which we can use the saddle point approximation directly. But as long as these are reasonably nice functions, we can deform it into the correct contour. But the fact that this saddle point approximation is applicable only if this is a constant phase contour tells us something about how we should deform the contour. In principle, there's many different ways that we deform the contour. Deform it, assuming that the poles don't get in the way, we could deform it to go through any or all of the saddle points. And in principle, those would give us different asymptotic expansions. One of those would be right. And if we keep in mind that this works only if we have constant phase contours, that will tell us which of the saddle points are relevant. So the key point is this. It tells us which saddle points are relevant. Once we know which saddle points are relevant, we can forget all about the phase. It doesn't enter any complication.
So to illustrate that idea, and also to illustrate another phenomenon that you may have encountered at the end of yesterday's tutorial, so you can test it again. Stokes phenomenon. We'll go through an example. So Stokes phenomenon is an abrupt change in the asymptotic relations as versus the phase of z changes. And this phenomena is best illustrated through an example. So let's look at an example and see how we can illustrate both this aspect of the saddle point approximation as well as this aspect of determining which saddle points are relevant. In the example we'll look at, is that I of z integral of e to the minus 4 z squared cosine phi dt and we're going to look at this as z goes to infinity. We're now with 0. So is this of a form we looked at before?
Yes.
Next. Okay, so we've got an exponential, something that depends on z, some other factor up front. Before, the crucial point was that this g was independent of z. So as we took z to infinity, this didn't become more important, and we could basically just ignore that for our derivation. Here we've got some z dependence in this factor. So may cause a problem, and well, you might still think, okay, as z goes to infinity, this thing is getting sharply peaked, so maybe we can just forget about that. So let's try that. So if we just neglect the cosine, the magnitude of the cosine isn't getting any bigger. Then we might say that I of z is like integral minus 4 z t squared, which is root pi over 16z. But you might suspect this is wrong. This is oscillating more and more wildly as z gets bigger and bigger. So we might expect there's some disruptive interference, and in fact there is. So in particular when t is like 1 over z, 1 over root z, which it will be, because we're integrating t from 0 to infinity, no matter how large z is, there'll be some region where t gets, we get this order as z goes to infinity. Then the argument of the cosine is not small. And so this is oscillating very rapidly and will leads some destructive interference. So we expect it to go to 0 faster than this because of destructive interference. And so we need to massage this integral to put it in that form. The key property of this form is that this prefactor doesn't depend on our expansion factor. So to do that, we can write, well, we can note that this is like the real part of a complex exponential. So we can write this as the real part of e to the minus 4 zt squared plus 5 zt minus 5 zt cubed. By symmetry, that's half integral from minus 1 to 1 dt to the minus 4 dt squared plus 5 dt. So now this is a correct form. We can identify just pull out a constant factor minus 2z. This is the integral e to the z rho t, where rho t is minus e minus I squared minus I e minus I. So now it's in the, certainly the form number 4. The contour is just a simple real contour that goes from minus 1 to 1. All of the expansion parameter dependent terms are in the exponent. So we know there won't be any destructive interference from the prefactor, which was something that we implicitly used in deriving Saddle-Point approximation. So we can apply the Saddle-Point approximation to this example as long as we can find appropriate constant phase contours.
Yeah.
Okay, so well, we want to use the Saddle-Point approximation. We need to figure out where the saddle points are. So rho prime t is 0. So if t is equal to I, or t is equal to 5i, these are our settings. So let's start a picture of what's going on here. So real and imaginary E-plane. What we have are two boundary points of our original contour. At -1 and 1. our original contour. Goes like this. And we have two saddles at I and 5I over 3. And so we certainly can't use a saddle point approximation if this original contour doesn't pass through either of the saddles. So what we need to do is figure out which of these saddles are relevant. And we can do that by looking at what the constant phase contours are. So constant phase contours are determined by the imaginary part of the rho. And so we can write this if U is real part of T and T is the imaginary part of T. So just 3UV is 8 plus 5U minus U cubed. Just plug T equals U times E into this equation and take the imaginary part. We'll get it. And so the first thing we notice is that the phase at our two endpoints are different. So the imaginary part of rho minus 1 is minus 4. Imaginary part of rho 1 is 4. So if we look at the constant phase contours that pass through the endpoints, they'll look something like, they're different, and they'll look something like this. So, a lot of these I'm not again, I'm just sketch what the result are. And we can do the same thing and plot the constant phase contours that pass through the saddle points, because after all, we want to deform our original contour to something that passes, it's equivalent to our original contour, but passes through one or both of the saddle points. We do that, it looks something like this, and like this. And so, based on the sketch, you can probably guess which contour we want to deform this purple contour into. And which contour is that? And someone say I, so we want to go through I, and why is that? So we can go around here, come back, infinity over here, go through I, and then come back over here. Because our function is analytic, we can deform a contour however we like. And this contour, this whole contour, this contour is, we can continuously deform into that contour without passing through any poles, so the integral along both of these contours is the same.
So this constant phase analysis tells us that we should do a saddle point approximation around this saddle point and not this saddle point. Okay. So that's our contour. So there will be, we can use our formula on the top board to get the contribution from the saddle point. This contour also has endpoints. And in general, we need to worry about the endpoints. And to see why, so remember that these constant phase contours are also the contours of steepest descent of the real part of rho. So in this direction, the real part of rho is decreasing. And so that means in this direction, the real part along this part of the contour, the real part of rho is decreasing, and so it's increasing in this direction. So along this part of the contour, the integrand is getting larger and larger, and it reaches its maximum value at the endpoint, and the same over here. So we don't expect that we can neglect the contributions at the endpoints in this case. Okay. And so we need a way to figure out the contribution of the endpoints. And there is a formula for it. I won't derive, but state go this way. So, x for the integral of this form. Then it's asymptotic as infinity. F over Ix psi prime. E to the I x psi of t. And so for those of you who are familiar with this is generalization of the Riemann-Lebesgue lemma. So which says that integrals of this form go to 0 because of the destructive interference, basically. And if you integrate by parts, you can get this term and the it's the consequence. Or it can be shown that these boundary terms go to 0 more slowly than the other term in the integration by parts. So this works as long as the right-hand side is non-zero. Everything is differentiable. Everything is continuous.
continuous and at least once differentiable, and the integral of the absolute value of f is finite. And so it's not constant. These are all the case here. So from this formula and our saddle point formula, we can determine the contributions of the two endpoints in the saddle point. So the saddle point contributes 1/2 e to the minus 2z pi over z equals +1 or -1, contribute 1/2 e to the minus 2z e to the z plus or minus 1. Sorry, I'll write the final result. Minus plus I plus or minus 4, 68z e to the minus 4z plus or minus 4iz. So those are the contributions, just applying this formula, the saddle point formula. And what we see is that as z goes to infinity, at least if z is real, then the contribution of the saddle point is much larger than the contribution of the endpoints. So I of z is asymptotic to 1/2 e to the minus 2z over z as z goes to infinity if the argument of z is 0. This will go like e to the minus 2z, which goes to 0 much more slowly than e to the minus 4z. Now what about if the argument of z is non-zero? We expect this relation to hold for if we go send z to infinity with a fixed phase, non-zero phase. So we're imagining that z is a now complex parameter. Is e to the minus 2z much greater than e to the minus 4z plus or minus 4iz. Z goes to infinity. Z non-zero. Is that necessarily true? How many think it is? 1. How many think it isn't? 2. Well, it's undecided. Let me give you a minute to make a decision. Made a decision? How many think this is true? 1 if it's true, 2 if it's false. I think it's reached a consensus. Yes, in fact, this only works in some wedge in the complex plane. All right, so if particular so what we're interested in is the limit as z goes to infinity of e to the minus 4z plus or minus 4iz over e to the minus 2z, which is the limit e goes to infinity of e to the 2 plus or minus 2I minus 1z. And we want this to be 0. So this will be 0 if the argument of z is less than arctan of half. Then we'll have a negative real part in the exponent. So in this region of z, the saddle point dominates, otherwise one of the endpoints will dominate. So this dominates if RZ is less than 10.5, and otherwise one of these will dominate. Okay. So this is an example of what's known as Stokes phenomenon. So if we change the argument of z, we get an abrupt change in the asymptotic behavior. So if in this wedge in the complex plane, the integral behaves like this for large z, otherwise it behaves like this. And change abruptly depending on the phase of the expansion parameter. Now, you may not be entirely convinced by this argument because we left one key step out of one key step out, and that's that. Well, if we change the phase of z, we also change what the constant phase contours look like. So those will change depending on what z is, and what will happen if we give z the argument of z to be 135 degrees. Constant phase contours will look something like this. Again, apply to this on Mathematica. And our poles are up here. Our saddle points are up here at I and 5I over 3. So the constant phase contours may pass through different saddle points depending on the argument of the expansion parameter. The constant phase contours will rotate and shift, and they may pass through some saddle points for some values, of the argument of z and not for others. And in this case, there are no saddle points if we take the argument of z sufficiently large. For this particular problem, this jump in which saddle points are relevant to the problem occurs after the exchange of dominance between the saddle point and the endpoints. So that these results are correct even if my first argument for them watertight. But in general, this exchange or jumping of the saddle points on or off the relevant contours can occur when the saddle points are the dominant contribution. So if you're looking at saddle point approximation in the complex plane, the relevant contours can depend on the phase of your expansion parameter. And for a sufficiently large angle, there are no cells. So Stokes phenomenon refers to this abrupt change in the dominant asymptotic behavior, and it can occur for two reasons. Either exchange of dominance between contributions of saddle points or endpoints, or it can occur because of an abrupt change in the contours, which tell us which saddle points are relevant. And so first, any questions on that? Yes, Katie?
So the saddle point approximation, it seems like the whole point is that you can just look at the saddle points and ignore everything else. But here we're saying that there's some other points that are important. So how often does that happen? And like, how would you know that you had to consider those points if?
So if you're using the saddle point approximation, the only case any other points can be relevant are if there are boundaries to your integration contour. The most common case in physics is that we're integrating from -infinity to infinity or 0 to infinity. So in -infinity to infinity, you don't have to worry about it, but if it's from 0 to infinity, you do. There might be a contribution from the endpoint that could be important. So it's never going to be the case that something that's in the middle of your contour that's not a saddle point will be relevant. It will either be an endpoint or a saddle point.
This equation you've written up here, is this only true when the endpoints dominate, or is this true in general?
This is only true when the endpoints.
Because you didn't mention, is that implied by some of those conditions you've written down? Or?
Let's see. Okay, so it's assumed here that we had boundaries. So what happened to our contour was that it had boundaries at some finite value and at -infinity. So if you have a contour like this, it doesn't have a saddle point. So if we look at this entire constant phase, contour, it has to be either monotonically increasing in this direction or monotonically decreasing. It can't have a local maximum for the real part. So
This boundary point is always going to be dominance. Will always be the dominant contribution like that if there's no saddles on that constant phase contour. If we had a saddle on this point, we'd also in general need to include that contribution.
So this is just for those two like half contours down the bottom, not the big one that arcs through.
Yes, this is assuming that there's no saddles on that part of the contour. Which I think is covered by this part that it's not constant. It shouldn't be constant anywhere. So for this example, we just plotted the constant contours, constant phase contours by hand and could, by eye, guess which saddles are irrelevant. I won't go through the details of it, but there is a general procedure for figuring out which of the saddles are irrelevant. So I've drawn here the constant phase contour that passes through this saddle. So that's the direction of steepest descent of the real part of the exponential. The direction of steepest ascent will be some contour that's perpendicular to that. So what you notice is that, or what you can guess, is that the steepest ascent contour passing through this saddle, it'll go something like this and pass through our original contour. And up to some subtleties about whether when the steepest ascent contours pass through other saddles. That's the general rule for which saddle points will contribute in the saddle point approximation. It'll be the saddles whose steepest ascent contours pass through the original contour. So there's a general procedure there that can be generalized to higher dimensions too. Won't go through that in full detail, but for simple examples, you can guess by eye. For more complicated examples, you can use that formulation. Okay, so sorry. What we've seen last couple of lectures is that we can approximate integrals using Gaussians, and that the result will be asymptotic. So a key step in this derivation is swapping some integral, which can ruin the convergence of a series. But nevertheless, assuming we're willing to get an asymptotic series approximation to what we're interested in, we can do that. All we have to do is force our integral to look like a Gaussian integral. And we can do that by, in the general case, by identifying the saddle points of the function in the exponential of our integral, and then looking at constant phase contours to determine which of those saddle points are relevant. And this is a technique
we're going to use over and over again in quantum theory and QFT2. Also other courses. But the basic idea is exactly the same. Those will be multiple integrals, actually infinite dimensional integrals, but just you think back to these simple one-dimensional examples. What we're doing in those cases is essentially the same thing as what we're doing here. Force everything to be Gaussian. Do the Gaussian integrals, and what we'll get is an asymptotic expansion. It tells us about how our functions we're interested in, say correlation functions in quantum field theory, depend on our constants. So that's what we've done, and where we're going tomorrow. So we'll look at in more detail about how to interpret the results of these integrals or any other divergent series that we encounter in physics. So often something we want to do in physics is we want to sum a divergent series, whether it's an asymptotic series or something else, like in the Casimir effect. And so tomorrow I'll argue that it is something that makes mathematical sense to assign a finite value to a divergent series. Clearly you're not going to do that just by summing up all the terms in the series, but there is a way in which we can assign some meaning to a divergent series, and we'll also discuss how we can interpret what these asymptotic series will get by using this saddle point approximation we'll need. So that's where we're going. Are there any questions? Yes.
It's just about the saddle point thing. I totally understand you use the remember again. How is it possible that the term right here is always that basically it's only the endpoints that contributes and not the middle of the integral? Because then at some point you're saying that the endpoints contribute much less than the saddle point, which has to be represented by something.
So a key assumption here is that this function's psi is not constant anywhere. In other words, it's monotonic. So
yeah, but in that case, it's not the case in the case we're considering. So what are we?
It does work on this part of the contour, the part that goes from infinity to -1. So for that part, we can use this formula. For this part that goes through the saddle point from infinity to infinity, we use the saddle point approximation. We can't use that formula. And then for this other part, we'll use that formula.
So basically we're evaluating the first and third parts of the contour with respect to the boundaries and with respect to the saddle point, and then we're comparing them.
That's right. Okay. Any other questions? I'll see you tomorrow.